Okay, so what I want to do today is I want to talk a little bit about equations of lines, dot product, cross product, equation of planes, and as time permits, determinants, areas. Probably won't get to matrices. At some point when we have free time, I want to talk a little bit about matrices. All right. So a couple of you have some suggestions of things you want me to cover today. If I forget to cover them, just please, let me know right now. So the first is the dot product. So we have two vectors, V is V1 through Vn, and W is W1 through Wn. Then V dot W is V1 W1 plus Vn Wn. This is a really nice expression to work with. If I give you any two vectors in Rn, I can combine them, and I'm combining them in a really nice way. I'm just multiplying and adding. I can do this in 2 dimensions, 3 dimensions, 4 dimensions, no problem at all. And it turns out the dot product has a really nice interpretation. V dot W is the length of V times the length of W times the cosine of the angle between V and W. So here's V, here's W, here's theta, VW. And again, one of the things that should be nice is V dot W should be the same as W dot V because multiplication is commutative. And since I'm talking about the angle between them, well, the cosine of theta and the cosine of negative theta are the same. So this is very easily seen to be the same as W dot V. And then in the lectures, we go through a proof as to why is this true. Sometimes what you can do is you can try to build intuition by looking at special cases. If you had to choose a special case, what could you assume about the length of V without loss of generality? To make your life easier, what could you assume about the length of V?
That's a real number.
It's a real number, but what kind of real number? What's a good value for it to take?
Rational.
Okay, but not more than just a rational, a specific rational. One. If the length of V is 0, there's really nothing to prove. And it's easy to see that if I triple V, I triple every component. So I would then triple the sum. And so we see if we place V with A times V, then AV dotted with W is just A times V dot W. So without loss of generality, we can assume if we want the length of V is 1. We could also, if we wanted to, assume that the length of W is 1. If one of them has length 0, there's nothing to prove. So if there's 0, okay. What direction would you want V to be to make things nice for you? If you could choose a direction for V, what direction would you choose? I can think of 2 natural directions for V.
The right.
Okay, so what would be the components of V?
1, 0.
Good. Special case. V would be 1 and then all zeros. And so if we do it in that special case, then you can go through and see that it's going to work out. At least in the plane. At least in the plane, it's not too bad. If you know linear algebra, it turns out that you could then get the general case by using rotation matrices. This is similar to, if you remember your calculus, you have the mean value theorem. And the mean value theorem says that there must be some point in time when the instantaneous speed equals the average speed. You can prove this by doing a special theorem called Rolle's theorem, which has the additional fact that the initial and the final speeds are 0. Or the initial and final distances are 0. So the average speed is 0. So if you can prove it in the special case of Rolle's theorem, you get the mean value theorem in general. With linear algebra tools, if you prove it in this case, you get in general. Does anybody remember what the main ingredient was in proving this? what trig result did we need? The law of cosines. So the input for the dot product formula is the law of cosines. And this generalizes Pythagoras. So if I give you, A, B, C, and we often use capital letters to denote the angles, then C squared is A squared plus B squared minus 2AB cosine of big C. So this is the law of cosines. How do you think you prove this? What do you think we have to reduce this to? Yeah, prove by making right triangles. Prove by drawing lines and making lots of right triangles and using Pythagoras. And now we can see a little bit of why I cared so much at the beginning of the semester to talk about the Pythagorean theorem. It's not just to find distances, but the Pythagorean theorem actually gives us this. Well, the Pythagorean theorem is a special case of the law of cosines. So what would be going on for the law of cosines if I want to use this for Pythagoras? What quantity would take on what value? So I wanted to use this for the Pythagorean theorem. Take a shot. Yes. So if C equals 90, cosine of C equals 0, and you get Pythagoras. So it reduces to the Pythagorean, which is good. It should reduce to the Pythagorean theorem. A squared plus B squared equals C squared. Excellent. So this is the dot product. And again, if people want to, I'm always happy to go into great details and prove. I am a theoretical mathematician, first and foremost, love proofs. But again, the proofs are there, the proofs are in the book. We can use the time a little bit more effectively. The main thing is the dot product allows us to get a little bit at the geometry of what's going on. That if I have two vectors, I want to understand what is the angle between them, the dot product helps. It turns out you can generalize this greatly if you continue in mathematics or physics. And instead of using vectors like Rn, you can use vectors that are functions. And you can actually talk about what is the angle between two functions. And so there's ways to interpret stuff like that. All right, so this is the dot product. The next is the cross product. And the cross product is a little bit harder to explain. The cross product really only works well in three-dimensional space. The cross product also is an example where order matters. In normal multiplication, 3 times 4 is the same as 4 times 3. It doesn't matter which order we do it. Can anybody remember a pair of mathematical objects where the order matters? Where A times B is not the same as B times A. A and B are typically matrices. So in general, matrix multiplication is not commutative. A times B is generally not B times A. You've got to be careful, order matters. The cross product order matters as well. So we typically use what's called the right-hand screw rule. Do you have to use the right-hand screw rule? No, but everybody else in the world typically does, and you want your notation to match. This is one at least where there's really no dispute. Everybody does this. In terms of spherical coordinates, the physicists and the mathematicians have different notation, and you've got to be careful. You've got to look at the book and see how are they defining them. If you keep going further, there is something called the Fourier transform, and there are 3 different ways of defining it. And it's even more enjoyable to try to figure out which notation are they using, because a lot of times they just say, we compute the Fourier transform, or which one is it? So what it's typically done is you have your fingers going from one vector to the other, and then the thumb points in the direction that they go, that the new vector. So if I take 2 vectors, second. and we've got somebody at home. So, here is two vectors. And what I do is I set it up so that my hand goes from V towards W. And then my thumb is pointing up perpendicular to V and W. And that's the direction of V cross W. So the cross product gives you something perpendicular to the two vectors. Okay. So we'll get to this in stages. So here is V, here's W, and here is V cross W. And it's perpendicular to both of those. But if you think about it in three-dimensional space, it actually works out perfectly. If I have two lines, that's going to give me a plane, typically. And then there'll be one direction perpendicular to the plane, and that's going to be the direction of the cross product. If I go in the opposite direction, W cross V, it's going to be going down. And so V cross W is going to be negative W cross V. That's going to go down. Then the question is, of course, what is the magnitude? This is just giving me the direction. The direction is perpendicular. What's the magnitude? And the magnitude of V cross W is the area of the parallelogram spanned by V and W. So this is V, and this is W. Then over here, this would be V plus W. And it would be the area of this object. So there's a nice geometric interpretation of what V cross W is. So both V dot W and V cross W have nice meaning. The question, of course, is there an easy way to find what this area is? And so if I give you two vectors, do we know any way to find the area of the parallelogram? And again, what we could do is we could play a game and say, let's start off with simple vectors. If I double V, what happens to the area? It doubles. If I triple V, what happens to the area? Triples. Okay, so I might as well assume V has what length? 1. And if I want to make it really nice, what direction should I choose V to be? Yeah, so I could build intuition by taking V to be 1, 0, 0, 0. I could start playing a game like that and try to build some intuition. Now, one of the things that's nice is even if I'm living in 20-dimensional space, V and W is still going to form a two-dimensional object of plane. So if you know a lot of linear algebra, you could actually always play some games and reduce this to, I just need to understand what's going on in 2 dimensions. So let's try to figure out what is area. So area of the parallelogram. So here's V, here's W, here's my parallelogram. Does anybody remember the formula for the area of a parallelogram? Base times height. All right, so I need to know the height. So how would I find the height? Well, if this is theta, then we get the height is just the length of W times what? Times the sine of theta. So the area is base times height is going to be the length of V times the length of W times the sine of theta. Okay. I don't know any formulas for the sine of theta involving V and W, but I do know a formula for something else involving theta in terms of V and W. What do we know? So what do we know that's similar to sine of theta in terms of V and W? The dot product. So we know V dot W is the length of V, the length of W, times the cosine of theta, and cosine of theta, well, how can we get from sine of theta to cosine theta? Yeah, sine of theta is the square root of 1 minus cosine squared of theta. So we can now put this in. And we can look at VW sine of theta. We bring that inside. And so we get the square root of the length of V squared, the length of W squared, minus the length of V squared, length of W squared, cosine theta. That's going to just be V dot W squared. And so when we substitute in, this is what we get for the area. And this is an expression that we can actually work with. V squared is just going to be V1 plus V2. So V1 squared plus V2 squared. Length of W squared is going to be W1 plus W2 squared. So this is going to be the square root of V1 squared plus V2 squared, W1 squared plus W2 squared, minus V1 W1 plus V2 W2 squared. Is everybody comfortable so far on the algebra we have, trying to find? Pretty comfortable as to how we got to here. All right, so now we just want to keep working with this expression. All right, so this is going to be the square root. Okay, so what do we have? Well, we have V1 W1 plus V2 W2 squared. We're going to get a V1 squared W1 squared. That's going to cancel with the V1 squared W1 squared. We're going to get a V2 squared W2 squared. That's going to cancel with the V2 squared W2 squared. We're going to have a V1 squared W2 squared term that's going to survive. We'll have a V1 squared W2 squared plus a V2 squared W1 squared minus twice V1 W1 V2 W2. So just when I do the algebra, a couple of terms are going to cancel. And so I guess this is now why I played the Beethoven early. That when we heard Beethoven, da 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 da, even with my bad singing or humming or whatever, you can identify that that's Beethoven. That's how great the music is. Fifth of Beethoven, people are not as familiar with disco, but once you know to listen to it as Beethoven, you can kind of hear it. So much of that is finding the right way to look at this. I can write this as V1 W2 squared minus 2 V1 W2 V2 W1 plus V2 W1 squared. All I've done is I've just rewritten things in this. What is this equal? You're back to the inside. Yes. Not times V2W1. Not plus. Minus V1W2 minus V2W1 squared. Square root. Oh, okay. So I'm taking the square root of a square. And so, this should be basically like the absolute value of V1 W2 minus V2 W1. And that's the area. Okay. So again, having some idea of how to do the algebra really helps. If you don't see this factorization, no problem. you can use the method of divine inspiration. If you just write it down, you can check and see, well, what do I get if I expand that out? Oh, I do get what we had before. And again, just knowing the answer, I know how to factor things a little bit. Also, having spent 3 decades, 4 decades now, doing problems like this, you eventually start to see how you should attack something like this. But why is this useful? We have V1W2 minus V2W1. And so we're going to define the determinant as follows. If I give you a matrix V1, V2, W1, W2, the determinant of that matrix is V1, W2 minus V2, W1. Or typically, if I give you A, B, C, D, the determinant is going to be A, D minus B, C. I can define anything I want. The question is, when am I defining something that's useful? I'm defining the determinant of a 2x2 matrix to be the product of the two things on the main diagonal minus the product of the two things on the opposite diagonal. Why is this useful? Well, we just saw that in the plane, this is giving me the area of the parallelogram generated by the vector that's the first row and the vector that's the second row. So there's a connection between determinant and area. So connection in plane between a determinant and area. So if I give you the vectors V and W, then V1, V2, W1, W2, the determinant of that V1, W2 minus V2, W1 is the signed area. And why do I say signed? Well, if I flip the order, if I do W1, W2, V1, V2, it's now going to be W1, V2 minus W2, V1, which is negative V1, W2 minus V2, W1. So the determinant is a signed quantity. If I flip the order of the two vectors, then I flip the area by a minus sign. It turns out that the determinant is one of the most useful ideas we have in linear algebra. In a lot of my classes, they're always, you want to guess, what do we need to go further? This is one of many times when I'm going to be appealing to, it would be wonderful to know linear algebra right now. If we knew linear algebra, it would be a lot easier to do all of these discussions. When we wanted to prove these theorems, it would be enough to prove them where one of the vectors is lining up with the x-axis, and then we appeal to, and now we just rotate and we see that things don't change under rotation. Over here, it would be wonderful if we actually knew what a determinant was. This is why when I was a freshman, there was a wonderful year-long course at Yale where we did linear algebra, multivariable calculus, a little bit of point set topology and vector analysis, all in one course. Because it's so much easier if you know the language of linear algebra. So we're going to be a little bit confined in terms of what we can do because we're not requiring linear algebra right now. But if you take linear algebra after this, hopefully you can then go back and say, okay, that's what's really going on. So we have a definition of the determinant in 2 dimensions. It is the area of the parallelogram created or spanned by the two vectors. How would you define determinant in 3 dimensions? So we give you the determinant of VW, let's go UVW. So we have U1, U2, U3, V1, V2, V3, W1, W2, W3. What would you like that to represent? Yes, volume. So this is the volume of the parallel pipette. And here's U, here's V, and here's W. And it's going to be something like that. So it's going to give us the volume of the parallel pipette. So then the question is, can we go through and come up with a formula that's going to give us the volume in that case? And if you think about it, well, if I have U and V, I can figure out what the area is of the of the parallelogram in the planes U and V. And then for W, I just see what's the height. And then the volume of the parallelepiped is the height times the area of the base. And so there's a way to motivate all of this. And what we're going to do is we're going to just say, here's what the formula is. So if I give you, this is just a trick, only works in 3 dimensions. If I give you U1, U2, U3, V1, V2, V3, W1, W2, W3, and you want to calculate what is the determinant, you rewrite the first 2 components, V2, V2, W2. And then what you do is you multiply and add diagonally with a plus sign for these, and for the other ones, we do it with a minus sign. So it's going to be U1, V2, W3 plus U2, V3, W1 plus U3, V1, W2 minus U3, V2, W1 minus U1, V3, W2 minus U2, V1, W3. That's going to be how we define the determinant of a 3 by 3 matrix. And it turns out that gives us the volume. We're going to use this to define the cross product. And we're going to use the following bits of notation. So I hat is the vector 1, 0, 0. J hat is the vector 0, 1, 0. K hat is the vector 0, 0, 1. These are 3 very important vectors. It's 1 unit in the x direction, 1 unit in the y direction, 1 unit in the z direction. Why is this bad notation? What's bad about this notation? What if we had to add another dimension? What would we do next? So we had to do one more dimension. What would we do next? We have I, J, K, L. Okay, and what if we had to do another one after L? M. What if we had to add 1,000 more? We've now run out of letters. And so a lot of times, instead of using I, J, K, we use E1, E2, E3. E stands for Euclidean. It's the standard plane geometry that we're using. And the nice thing about this is we have to add more directions. It's not a big deal. We can just add higher and higher subscripts. If we use the letters I, J, and K, it can get hard because we start to run out of letters. So either one is fine. A lot of times books like to use I, J, K because we're focusing on 3 dimensions. And you can quickly look and see what's going on. And so the following is how we calculate the cross product. And it basically, it's a mnemonic device. Anybody know what Holmes means for mnemonic? It's the lakes, Huron, Ontario, Michigan, Erie, Superior. Most voters earn money just showing up near polls. Planets. Although nowadays you can't add Pluto. Pluto has been downgraded. So there's certain mnemonic that just help you remember things. Sarkatoa, which for me, I always have to rederive the expression by knowing trigonometry, which is not how it's supposed to be. But so here is a way to remember the definition of the cross product. It is highly illegal. You see somebody, oh, yeah, let's do it. I hat, J hat, K hat, V1, V2, V3, W1, W2, W3. I should not be allowed to do this. I'm taking my determinant, and I'm supposed to just put in 3 rows of numbers, and the first row I'm putting in vectors. So we write again, I hat, J hat, V1, V2, W1, W2. And then we do the product. So it's going to be I hat, and when we go down, it's going to be V2W3 plus J hat, it's going to be V3W1 plus K hat, and it's going to be V1W2. Now we have to do going in the other direction. I could start off with the K direction, but I'm going to start off with the I and put them under each. It's going to be minus I hat, and now it's going to be V3W2 minus J hat, and it's going to be V1W3, and it's going to be minus K hat, V2W1. And now I'm going to just collect the I's together, the J's together, and the K's together. So it's going to be V2W3 minus V3W2, I hat. Now for the J hat, it's going to be plus V3W1 minus V1W3, J hat, plus V1W2 minus V2W1, K hat. Or if you want to write it as a vector, V2W3 minus V3W2, comma, V3W1 minus V1W3, comma, V1W2 minus V2W1. If you look at this, you can see there's a lot of symmetry going on. Each one has a minus sign. Each one has a difference of two terms. Each term involves a V and a W, and they go in opposite order. It goes V2W3, then V3W2, V3W1, V1W3, V1W2, V2W1. And if you look at what's going on, the first one is always the V, the second one is always the W. We start with the next number from the component that we're missing. So the first component is the first component. What's after 1, 2? We do V2W3. The next one is the second component. So we start with V3, V3W1. The next one is the third component. What's the first index after 3? We wrap around and come back to 1. So it goes, you miss 1, you miss 2, you miss 3. So you're missing the index corresponding to which location you're in. And you just start with the next available index. So this is the formula for the cross product. It turns out to be extremely useful because it's perpendicular to V and W. Okay, so theorem, V cross W is perpendicular. And so if you remember your geometry, that's the symbol for perpendicular to V and W. How can you prove that two things are perpendicular? How would you prove two things are perpendicular? What would it mean for two things to be perpendicular? They intersect at a right angle. And so if they intersect at a right angle, what can you tell me about a certain thing associated to them?
The dot product.
Yes. So show V cross W dotted with V equals 0. That would imply the cosine of the angle is 0, which implies that theta is 90 degrees. Well, it could also, of course, be 270 degrees, but that's just other orientation. Yes.
It's done on homework, right?
Could be.
Or like,
So you just go through, roll up your sleeves, and you do the calculation. There's a lot of algebra, but you just have to show at the end of the day that everything cancels out and you get 0. Okay. Then you can start to ask lots of other different relationships. Can I study U cross V cross W? Does that make sense? What kind of object is U cross V?
vector.
It's a vector. So does this make sense? Yes. Could we study U cross V dotted with W? Yes. So both of these make sense. And it turns out that one of them is actually related to those two. U cross V dot W is related to the volume of what's going on. And so again, the reason the cross product is so useful is it gives us a direction perpendicular to the two vectors that we have. Why do we care so much about this? Well, let's go back to lines and planes. So last time we talked about the equation of a line, maybe P of t is equal to P naught plus t times some vector. So maybe you have x of t, y of t, z of t is equal to x naught plus t v1, y naught plus t v2, z naught plus t v3. And so this is one way to write the equation of a line. So the book talks about a symmetric version. For the symmetric version, we can solve for t in the first one, and we get, t is maybe x minus x naught over v1, t is y minus y naught over v2, t is z minus z naught over v3. If v1, v2, v3 are not zero. Now, if you think about what's going on, how many dimensions is a line? Line is one dimension. Once I give you a point, and I give you a direction, then the line is completely specified, and I just have to tell you how long do I flow? How many copies of that vector v do I take? So a line is one dimension. Once I specify how far I go, I know exactly where I end up. And there's a couple of ways of doing it. When I write, P of t is P naught plus t times v, it's very clear. Here's my free parameter, t. Here's my variable. Once I tell you what t is, I know where things are. Well, the other way of doing it is, well, what if I tell you x? If I tell you x, I can use this first equation to then figure out what t is. And now that I know t, I can then figure out y and z. So there's a lot of ways to go back and forth depending on what you're given. Some ways are more convenient than others. And so here, all three of them have to equal t. And so it basically tells you if I move this much in x, how much must I move in y, how much must I move in z. I like the P naught plus TV. I like just how this works. This is the equation of a line. Let's think about what's going on for a plane. So for a plane, here's my plane, and maybe here's some base point, and here's the origin down here. So here's the origin, here's my vector. Here's my vector P naught. So this is my initial point. And now if I'm in a plane, as long as I take two directions that are different in the plane, I can get to any point in the plane. So this is where Manhattan beats Boston by a tremendous amount. The grid of Manhattan, it's very easy to get along. You have your north-south, your east-west. With Boston, you have Beacon and Comm Ave crossing each other multiple times as to which one is on top. If I give you two different directions, here's my V direction and here's my W direction, you give me, some point over here, and I'll tell you, okay, I flow down some amount like this, and I flow some amount like that, and I can get to that point. So I can write down the equation of a plane, where am I? And now I have to give you two parameters, T and S. And it will be, where do I start? P naught plus T times moving in the V direction plus S moving in the W direction. So this is one way to write down the equation of a plane. I give you a point, my base point, and I just move some amount in V, some amount in W. And you can be any point in the plane, and I can figure out where I am. When you do linear algebra, this makes a lot more sense. We're not doing, of course, linear algebra, just trying to do enough. Let's unwind what's going on. So we have some points, say x, y, and z is our general point on the plane. It's equal to our starting point, x naught, y naught, z naught, plus t, v1, v2, v3, plus s, w1, w2, w3. So this is one way of writing down the equation of the plane. So we have two free parameters, t and s. And so we get x is x naught plus t v1 plus s v2. Y is y naught plus t v2. Oh, sorry, this should be. Over here, this should be w1 plus s w2, and then z is z naught plus t v3 plus s w3. So it all comes down to what are your free parameters. So we have to have two free parameters. Once I tell you x and y, is z determined? If we know x and y, do we know z? Has to be, right? This is a two-dimensional object. Once I give you x and y, z has to be determined. So if we know x and y, z is forced. Well, if we know x and y, we can solve for t and s. And then, knowing t and s, we know z. Is everybody comfortable that if we know x and y, we know t and s? And now that we know t and s, we know z. So we get, this implies, after you do some algebra, z is z naught plus some function of x and y, v3, plus some other function of x and y of w3. But we can solve for x and y. We have a system of two equations and two unknowns. And it turns out these are both going to be linear in x and y. And so the whole point is, after algebra, it's going to reduce to something like ax plus by plus cz equals d. And this is the equation of a plane. So you can rewrite this in the form ax plus by plus cz equals d, which makes sense. If I know x and y, then z is forced upon me. It turns out that there's a nice way to interpret what a, b, and c are. And so let's think about what's going on. If I give you a plane, so here's my plane, as always, here's my point P, here's my origin. So there's my vector P naught. Here's V, here's W, and I'm going to introduce something new. I'm going to introduce the normal. So a normal is going to be a vector that's perpendicular to the plane. So n is the normal. It is perpendicular to the plane. Do we know a way to find something that's perpendicular to the plane? So I give you, yes, we do. Yes, we could use n is v cross w. So this is really nice about living in three-dimensional space. So we could use v cross w to give us a normal. If you want a unit normal, we could use V cross W divided by the length of V cross W. If we wanted to have a unit, well, that's not a big deal. There's another way to write what's going on. So imagine I give you some point over here, and this is my vector, P is my generic vector x, y, z, which is some point in the plane. So imagine I have some point in the plane, and I want to come up with an equation that the coordinates x, y, z have to satisfy. Well, if I draw the line from P naught to P, so this is the vector P minus P naught, and then coming up over here is the normal vector. What must be true about the normal vector P minus P naught? If P is in the plane, what must be true about the normal and P minus P naught? They're perpendicular. Okay, so how do we use that? Well, that means the normal dotted with P minus P naught has to equal 0. So we get n dotted with P minus n dotted with P naught equals 0, where n dotted with P equals n dotted with P naught. And if we let the normal be A, B, C, and we get AX plus BY plus CZ equals D. We're just letting that be D. So this is a nicer way of getting to the equation of the plane. If I have two vectors, I can calculate in the plane, I can calculate the normal as long as the two vectors aren't in the same direction. If I give you V and 2V, that's not going to give you a plane. If I give you V and 2V, what kind of object does that give you? So I've got V and I've got twice V. It gives you a line. So I need to take two vectors that are not in the same direction. As long as they're not in the same direction, it's fine. What would be a good choice of two directions? Perpendicular. That's why Manhattan's grid is so nice. It doesn't have to be perpendicular, but it makes things nicer. But as long as they're in different directions, that's fine. So if I give you V and W, I can calculate the normal. Well, conversely, I could just say, here's the normal. I want a plane that goes through this point, and its normal is 138. Well, if I give you 138, then you know what the normal is. And then you can just write, oh, okay, it's going to be 1 times x plus 3 times y plus 8 times z is then just going to be 138 dotted with whatever that initial point P naught is. So you always have to think, what information do I need to know? It's not enough to know the normal direction. I need to know a point as well. So this is another way of just generalizing what's going on. If you look at this definition of a plane, you can clearly see the lines living inside of it. If I have two lines, okay, that makes sense that they should both be in the plane. So if I take t equals 0, I get one line. If I take s equals 0, I get the other line. I can see the two lines living. If I have a plane and it intersects with another plane, what am I going to get when two planes intersect? Typically, a line. Do every two planes intersect? No, I could have two parallel planes. And then did I send you Euclid's Fifth by Asimov to look at before the semester began on bias in mathematics? Euclid's Fifth postulate. All right, I will send that for you to take a look at it too. Just this geometry. If I have two parallel lines, they never intersect. If they're not parallel, they intersect once and only once. And just trying to figure out what all of this means. All right, so this is the end of the next class. If I did not cover what you wanted me to cover, just email me and let me know. Again, I am trying to supplement what's going on in the book and in the video that you're already watching, so that we can try to use class time as effectively as possible, so that we can really talk about why these things are true. I am, of course, happy to do a lot more proofs if people want to. Based on previous years, I am keeping it like this.